Hi guys, today we're going to continue looking at the normal distribution. This is in the strand of statistical analysis, which is in the Year 12 HSC aspect of the Standard 2 Mathematics course. This video is specifically going to look at the second dot point, which states that students have to calculate the Z-score, the standardized score, corresponding to a particular value in a data set. So in order to do that, we need to understand what on earth a Z-score is. So the correct definition for a Z-score, according to NESA, is that it is a statistical measure of how many standard deviations a score is above or below the mean. So let's break that down and actually understand what on earth that means. It pretty much means that if we have a set of normally distributed data, if I draw you a normally distributed data curve, and we have our data sitting along our x-axis, we also have a corresponding z-axis. Now we know from the previous video that our x-axis normally distributed data is symmetrical about the mean, which is given by x bar. A z-score is normally distributed about the mean also, but a z's mean is always 0. Now, this z-score here, let's interpret it. We have a z-score of 2.3. That just means that the corresponding x-score for this z-score is 2.3 standard deviations above the mean. And if we have a z-score of negative 4.2, that just means the matching x-score is 4.2 below the mean. So we can physically calculate this using a formula. And this formula is going to be given to you on the formula sheet in your HSC exam. So you don't need to remember it. You do need to remember how to manipulate it though. So here we have z is equal to x minus x bar, which we know is the mean, divided by s. S here is the standard deviation of the population, not sample, okay? There's a difference between the sample standard deviation and the population standard deviation. So let's take a look at actually calculating this. There's two types of examples that we're going to go through in this video. The first one is an easy example. The type of question you'll be given is to calculate the z-score if x is equal to 7, x bar is equal to 3, and s is equal to 2. In this case, you are literally given all the data you require to manipulate the formula. So your formula, which you'll turn to the back of your HSC paper and get from your formula sheet, is x minus x bar all over s. And now it's a matter of simple substitution. We place the 7 where the x is, the 3 where the x bar is, and the 2 where the s is. And we get 4 on 2, which then we can simplify down to z is equal to 2. Now, what does this look like graphically? If we have our normally distributed data, that's an absolutely horribly drawn bell curve. Let's try that again. So if we have normally distributed data, which is distributed around the mean, we've been told that the mean here is 3. And we are wanting to look at the data point of 7. This is our x-axis. We've now created a corresponding z-axis. Above we said that z is also normally distributed about the mean, where the mean is 0 for z. Here we found out that our score of 7 is equal to a z-score of 2, meaning that an x-score of 7 is 2 standard deviations above the mean. Okay, pretty crazy, pretty simple there, guys, all right? The second example that we're going to go through is a bit of a harder example. This is when you're not given the information, but rather you need to calculate it using a scientific calculator. So here we have our data of 2, 3, 3, 4, 6, 7, 7, 9. First things first, we need to figure out our mean. We can do this manually by using formula the sigma x divided by n, which just means the summation of all the data sets divided by how many data points there are in our data set. So add them all together and divide them by how many there are, and we end up with x bar equaling to 5.125. Point there. The next thing we need to calculate is our standard deviation. Now, we can do this manually using the formula standard deviation is equal to the summation of all x minus x bars squared on n, but that will take a very long time. Therefore, I'm going to pop open my scientific calculator. I'm going to type in my data. So I'm going to first of all go to stat mode. So I press mode, I'm going to stats, and I'm going to press number 1, and I'm going to enter my data. So I've got 2 equals 3, 3, 4, 6, 7, 7, 9. Now that I've entered my 8 data points, I'm going to press AC, Shift 1, I'm going to go to variance. Let's check if we got our mean correct by pressing 2 equals. Beautiful, we didn't make a mistake with our mean. I'm going to go back, press Shift 1, go back to variance. Now S is S of X, it's the standard deviation of the X data points. And I've got the S of X is equal to 2.47 to 2 decimal places here. The exam will specify how many decimal places you want, so don't stress too much about that. Now that we have all the information we require, we can go ahead and plug it into our data set. We know our formula is x minus x bar on S of X. Here, let's say we want to calculate a z-score for the data point 6, okay, for this following data set. So we're going to plug in z is equal to 6 minus x bar, which is 5.125, all over 2.47. Get up my calculator. I'm going to go back to computer mode, go to my fraction button, 6 minus 5.125 all over 2.47, and I'm getting a z-score of 0.35. Again, what does this look like graphically? If we have our x-axis, we have our normally distributed data. We had calculated our x bar to be 5.125. We have our corresponding z-axis, which we know the mean is 0. We wanted to look at the particular data set point 6, which we calculated was 0.35 standard deviations above the mean. So our concluding statement is that x of 6 is 0.35 standard deviations above the mean of 5.125. Hopefully that gives you a little bit of insight into how to calculate a z-score, what a z-score is, and what a bell curve with normally distributed data can be used for interpreting z-scores. The next video will delve even further into z-scores, looking at the percentage of the bell curve which is dedicated to 1 standard deviation and 2 standard deviations both above and below the mean. Thanks.